Muted again. I'm Jerry Stenbakken, retired from National Institute of Standards and Technology. And is there anybody I missed?
Yes, me.
Well, you're introducing the speaker, so you're
Well,
last.
yeah, I'm going to introduce him, not me.
Hold on.
Just me.
Okay.
Well, I'm Alan De Silva, retired from the University of Maryland, where I worked mostly on problems in thermonuclear fusion physics. Retired now since '97.
Wow.
Thank you, Alan. Anybody else I missed?
You're
Like
not
to know
going to
where
let
Jack
me
is.
introduce myself?
Okay, Don, why don't you go ahead?
Okay, I guess we caught everyone. Okay, I'm Don Novotny, and I'm retired from the National Institute of Standards and Technology, where my last 10 years I ran the semiconductor processing lab. So anyway, with that, let me introduce our speaker. The title of today's talk is Earth's Co-Evolving Geosphere and Biosphere. The story of Earth originates from the clumping together of dust from exploding stars to form planets and planetoids. Alteration of these planetesimals by water and heat resulted in the 300 minerals found today in the meteorites that fall to Earth. Earth's evolution progressed in a sequence of chemical and physical processes which ultimately led to the origin of life. Once life emerged, mineralogy and biology co-evolved its changes in chemistry of the oceans, of the atmosphere, and the Earth's crust dramatically increased the Earth's mineral diversity to the more than 5,800 species known today. It is possible that the formation of organic molecules and thus the origin of life might have evolved from the action of hydrothermal systems on these minerals. With that, let me introduce our speaker. Our speaker today is Dr. Robert Hazen, Senior Scientist at the Carnegie Institute of Science and the Robinson Professor of Earth Science, Emeritus at George Mason University. He received his BS degree and SM degrees in geology from MIT and a PhD from Harvard in Earth Science. He has received, among other awards, the 2021 International Mineralogy Association Medal, the 2016 Robo Medal of the Mineralogy Society of America, and the 2012 Virginia Outstanding Faculty Award. He is author of more than 450 articles. The biomineral Hazenite was named in his honor. He and his colleague have explored both mineral and evolution and mineral ecology, new approaches to that exploit the large growing mineral data resources to understand the co-evolution of the geosphere and the biosphere. With that, please welcome Bob Hazen.
Thanks
Clap,
so
clap,
much.
clap.
Yes,
Did I miss anything?
and we should say, now you can see my screen, I hope.
Yep.
Okay, great.
Very well.
Well, I'm just delighted to be able to talk to you about something that I'm very passionate about and just am enjoying immensely. And that's a direction in mineralogy that we call mineral informatics. And you might say, well, okay, why, if we're interested in these larger questions, would we resort to minerals? What are minerals? Why are they so important? And I'm sure you understand that amongst other things, minerals are absolutely fundamentally important. Here we go. Let's keep going. There we go. All right, got it. So minerals provide the raw materials. One of you mentioned you were involved in the steel industry. Well, of course, for all kinds of technologies, for agriculture, and indeed all life depend on minerals. So that's pretty important. it's also that minerals preserve a record of planetary history. So if we want to understand Mars or Mercury or the moon or other worlds, the minerals are really what tells us what's going on. And on Earth, of course, biological evolution is preserved in rocks and minerals. Minerals are really important to the foundation of solid state chemistry and physics, and many Nobel Prizes have been awarded, and things as fundamental as the periodic table and X-ray diffraction were discovered by the study of minerals. And for me, the reason I started getting fascinated and enamored with minerals when I was probably 9 or 10 years old and going to museums was that they're just amazingly diverse, and they're beautiful, and they can be stunning, and just sort of captures your imagination. But here's a point I really want to emphasize, that if you think about it, minerals, individual minerals, combinations in rocks are the oldest objects you can hold in your hand. There's nothing older. They can be 4.5 billion years old. And as a result, minerals are better than anything else. They tell the stories of the origin and the evolution of planets and of life. And you think about it, every specimen is like a time capsule. It's information rich, just waiting to be open, waiting to be read. So what I want to do today, it may seem like it's getting a little esoteric, but by the same token, this is really fundamental and it's part of any science. I want to review a classification system in minerals, and I'm going to propose a complementary classification system to the one that's been in use for almost 200 years. And in the process, this gives me a chance to introduce this idea of mineral informatics and show you some of the power of thinking about Earth and life in this way. So think about it. What are the objectives of a classification system, any classification system, minerals or whatever? And I think the first is pretty obvious. It's to create an organizational system so that you and I can talk unambiguously about the object in that system, whether it's plants or minerals or animals or planets or stars or whatever. You need to be able to classify them to talk about them. But in addition, a classification system, ideally, if you're doing it right, it can play a central role in the discovery and in the articulation of scientific theories. So there's a role. And because of these ideas, you can have multiple valid classification schemes. Each one of them can address a different theory or a different aspect of nature. And I'm going to be proposing one that's different from the current scheme. Now, what's the current scheme? The IMA, or the International Mineralogical Association, defines a mineral as a naturally occurring solid. It has an idealized chemical composition. So the photograph I'm showing you here is of quartz, that's SiO2. And it has an idealized crystal structure, in this case, the quartz structure. And every combination of chemistry and structure, every unique combination is a different mineral species. So that's a term of art in mineralogy. And right now there are about 5,800 approved by the IMA mineral species. Each one has a distinctive end member idealized composition and idealized crystal structure. So that's what we mean when we talk about mineral species. And this goes back to 1850, when the American mineralogist at Yale University, James Dwight Dana, published the 3rd edition of his system of mineralogy, and he emphasized chemistry and structure. And that sort of stuck. So when you think about it, these 3 criteria, naturally occurring, idealized composition, idealized structure, what that does is it defines minerals with the absolute minimum possible bits of information. If you want to distinguish diamond from quartz, from calcite, from pyrite, the minimum information you need is the idealized crystal structure and the idealized composition. And so that's what the IMA system does. It's absolutely essential. It's incredibly efficient. It's worked for almost 200 years, and I'm proposing something different to complement it. Because if we're going to understand the coevolution of Earth and life, if we want to understand how planets work, then you need a classification system that incorporates not only structure and composition, but also incorporates changes that occur to minerals through deep time. So time has to be a factor, formation mechanisms have to be a factor, and all that's revealed through the information-rich aspects. So why do propose a different classification system? Here's this idea of a parameter of time. Planets are these dynamic systems. The histories are recorded in the minerals. Minerals preserve information about the history. And that evolutionary system then has the potential to form the theories of planetary origin. There's a second. This is a more subtle reason why I think we need a different classification system. There's an idea in philosophy of science called natural kinds. And a natural kind is supposed to represent a genuine division in nature. Something that's independent of the way humans like to provide conventions or interests or action. And an example of natural kinds that's often cited is the periodic table. Each element, carbon is the element that has exactly 6 protons. It's different from nitrogen, it's different from boron. Every atom has an integral number of protons. That's the atomic number. And so each of the chemical elements is a natural kind. But in mineralogy, the minerals are never, exactly the end member composition or idealized structure. They always have defects. So this idea is that the idealized IMA species aren't natural kinds, but we might be able to identify natural kinds if we thought about nature and how nature makes minerals that are in a sense messier. So a third reason is that the evolutionary system, this new way of approaching mineralogy, allows us to ask questions in a different way, especially about time. So how does life emerge from non-living worlds? How did life evolve on Earth? Are we alone in the cosmos? These are questions that really are not amenable to the kind of classification system IMA has done, but we're trying to provide this new idea, a system that looks at information and looks at time. So here's this idea. The primary tangible evidence we have for the earliest process in the solar system and the evolution of our planet. There are information-rich rocks and minerals because every specimen is a time capsule. It's information-rich, it's waiting to be opened. And this is the key to understanding the coevolution of Earth and life. This is a field we call mineral evolution. And so what I'd like to do now is take you through sort of a history of the evolution of this idea called mineral evolution, which is probably what I'm best known for in the scientific world. And it sort of took place in 3 stages. The first, part 1, the years 2008, 2009, when we published a paper called Mineral Evolution. And it was an extremely qualitative story about how planets change as viewed from the mineralogy. And here, the soundbite, mineral evolution is simply the study of the changing diversity of minerals and the distribution of minerals. And that's a consequence because you have new kinds of physical processes, chemical processes, and on Earth, ultimately biological processes that create new niches for minerals. So mineral evolution is a change in the diversity of mineral species. It's the relative abundances of minerals. It's the compositional ranges of minerals. And it's even the sizes and shapes of minerals. All these things change through Earth history. Now, what we've done is focused exclusively on the near surface environment, the upper 3 kilometers or so. That's because that's what's accessible to study in the field. It's where you're most likely to see minerals on other planets and moons. And also it's where you have direct interaction with biology. And so you certainly could extend mineral evolution to the deep mantle or the core of Earth. Other people might want to do that, but we don't really have direct evidence that we do looking at near surface environments. So I have to make a comment here. I just have to sort of address an objection that has been expressed. Some people hate the idea of using the word evolution and minerals in the same sentence. And I disagree with this strongly. And I think that the word evolution has several meanings. The most basic one is change over time. And this has been used for more than a century in geology and astronomy, talking about the evolution of stars, the evolution of planets, evolution of, in this case, igneous rocks. It also, there's an implication that a system gradually becomes more complex, whatever that means. And if you look at biology through time, you look at mineralogy through time, you see an increase in complexification. Now, also, it's more than just increasing in complexity. It's congruency, that is, each stage follows from the previous stages. So there's a logical sequence here. And so those are all aspects of an evolving system. It's not this, though. And you need to put this out of your mind. It's not Darwinian evolution. There's no natural selection or common descent. So you can erase that from your minds. That's not what we're talking about here. And the basic idea of mineral evolution is new minerals formed through a combination of chemical, physical, and ultimately biological processes. And what we did in that very first paper in 2008 is we proposed 10 stages of mineral
Wait,
evolution.
could I call you back a little later? I'm in the middle of a listening to
I'm
an
sorry,
lecture.
if you would be willing to mute yourself,
Yeah.
whoever's
Okay, right. Bye.
thanks. So there's 10 stages of mineral evolution, spanned about 4.5 billion years. And this is a very qualitative, it's a narrative, which I think had a lot of power just because it told the story. Now, even before Earth formed, there were about 20 different kinds of minerals that were forming around stars. As an old star evolves, its envelope starts to expand and cool. It's rich in things like carbon and silicon, nitrogen, oxygen. And so you can form these very refractory high temperature phases. So those are the minerals, that's stage 0. And they basically have about a dozen different chemical elements and maybe 20 minerals. And so if you want to say, well, what's the mineral evolution story? It's the story of how you get from about 20 minerals with 12 essential elements to what we see today, which is more than 5,800 approved species with 72 different essential elements. And that's the mineral evolution story. 10 stages. Stage 1 is the earliest nebular condensates called chondrites, about 90 mineral species. Stage 2 is when you take all the chondrites, you bring them together, you make planetesimals, and you get up to about 50 to 100 kilometers. They start to melt. They start having a core and a mantle, in some cases a crust. You also get aqueous alteration, you get thermal alteration, you get impacts that create new minerals, and that gives you about 300 minerals altogether. Those 300 minerals fall to Earth today in meteorites, they fall on Mars, they fall on the moon. Every world in our solar system that has a surface is going to have these 300 minerals associated with meteorites. And we think that probably if you have a dry planet, the moon, Mercury, for example, those are probably a pretty good approximation of all the mineralogy you're going to see at the surface. Those are the minerals that planets can make if they don't have a lot of water around. But if you have water, and that includes early Earth and also Mars, you can get additional minerals through water-rock interactions, hydroxides and clays and ices and all sorts of things. That gets up to about 450 species. Our guess is this is probably the end point for Mars. And what we see on Mars today conforms to that idea. So you have a variety of processes that make minerals, but you cut off at about 450. Now, Earth, being a lot larger, and had some other tricks up its sleeve. And so you can partially melt the outer layers of Earth, a rock called basalt, which is the kind of black rock you see in Hawaii. If you partially melt that partial melt is much more silica rich and carries with it a lot of rare elements, and you can start making granites and also a whole bunch of rare minerals that have boron and lithium and cesium and some other elements. And so you get up to about 1,000 mineral species from that. And then on Earth, we even have more fluid rock interactions associated with what's called plate tectonics. So as Earth's crust and upper mantle, these rigid plates descend deep into Earth, they partially melt again. You've got huge volumes, hundreds of millions of kilometers, cubic kilometers of water rock interactions, and they form all kinds of new minerals, a lot of metal deposits, hundreds of sulfide and sulfosalt minerals, new high pressure minerals that are formed by bringing deep rocks up to the surface. And so this gets us up to over 3,000 mineral species. So Earth, just through pure physics and chemistry, can give us about 3,000 different mineral species. But remember, I said that we have more than 5,800 species on Earth today. So how is that possible? And I think the principal answer is life. That life leads to new minerals. And so we think about it this way. To me, this is such an interesting twist. Many, many people have studied the origin of life, and everybody says in some way or another, minerals had to play key roles. They could catalyze the formation of biomolecules, their reactants themselves, templates for separating and concentrating minerals. They protect molecules on mineral surfaces, and they can provide scaffolds to build larger and larger structures like polymers. So minerals played a key role in life's origins. But then it turns out, by a turnaround fair play, life played key roles in the origin of minerals. And this is one of the things I mean when I talk about the co-evolving geosphere and biosphere. So stage 6 is when life first popped up on Earth. It didn't make a whole lot of new minerals because those earliest microbes just exploited the chemical potential energy of minerals that were not in equilibrium with the surface. They'd come from deep in Earth and they'd sit there, and then the microbes would help to oxidize them, for example, and you'd get new deposits, new formations. So new kinds of mineralization, but not many new species. The game changer was when life figured out how to produce oxygen through photosynthesis, and that oxygen-rich atmosphere rusted the entire surface and caused literally thousands of new mineral species. This is stage 7. Think about copper minerals. All of these beautiful blue and green copper minerals wouldn't have formed before you had oxygen in the atmosphere. So maybe 2/3 of all the known copper minerals, maybe 90% of all the uranium minerals wouldn't form without having oxygen in the atmosphere. And there's literally hundreds and hundreds of other minerals of any redox sensitive element. So lots and lots of colorful minerals arose as a consequence of oxygen. That's stage 7. Stage 8 is a long period when the oxygen was building up in the atmosphere, but it had to fully oxygenate the oceans before you could do much more. And so this is a period called the intermediate ocean. Some people call it the boring billion, a period when not much happened, at least from a mineralogical point of view. There are stage 9, starting about 850 million years ago, was a period when we went through cycles of snowball Earth. And it got so cold on the planet that ice, glaciers, ice probably covered all the way down to close to the equators. And so by far the most common mineral at Earth's surface was ice. And then you'd have periods of warming when almost all the ice would go away, that is, ice went extinct, and then it would come back again when it got cold again. So these dramatic cycles was a period of about 300 million years called the snowball Earth. And then finally, we had the Phanerozoic biomineralization. This is the last 500 million years or so. Life goes on land. You get all sorts of new forming shells and teeth and bones, coal minerals, minerals associated with the decay of plants and animals, all different kinds of interesting things. And just a remarkable set of stories about how life and minerals interact. I've got to tell you one story, just a story about trilobite eyes, because to me, this exemplifies how amazing life is in using minerals to its advantage. Now look at those eyes. They're compound eyes, lots of little lenses. And every one of those lenses is made of a mineral called calcite, calcium carbonate. And calcium carbonate is a trigonal mineral, and the C-axis is pointing right out at you, so it is perfectly aligned little single crystals. But there's a problem, because pure calcite makes a terrible lens as a result of chromatic aberration. Red light and blue light bend differently. Everything is out of focus. It just doesn't work very well. But there's a solution. If you substitute for the calcium a little bit of magnesium, and if you do it just the right way, so the ratio of calcium to magnesium is zoned from the center of the lens radially to the outside, you can correct for chromatic aberration. And that's exactly what evolution has done. The trilobite eyes are not just calcite crystals, but they're calcite crystals that are radially zoned with magnesium substituting for calcium in a way that corrects for chromatic aberration. Now, if you were designed to task as an engineer to build a lens like that, it would be extremely difficult. But life figures out a way, because life selects for things that work, and that's what worked. So that's biomineralization. It's part of the coevolution of life and minerals, and it just amazes me. Okay, so that's the first stage of mineral evolution. And what we've learned is that Earth's near-surface mineralogy is diversified dramatically over this period of time. It's characterized by a whole sequence of new mineral-forming processes, each of which, if you think about it, explored a new range of pressure, temperature, composition, time, that sort of thing. And therefore, the biosphere has been a major factor in the diversification of minerals. This is part of the whole story. So what did we learn from this first stage? Well, this represents a new way of framing mineralogy for education and engagement. And to me, this is one of the most extraordinary things. Now, I got to take you back to my childhood, 60 years ago. when my family moved to close to New York City, and I started going to the American Museum of Natural History in New York City. And I just fell in love with their mineral collection. It's called the Morgan Hall of Gem and Minerals. All the minerals were arranged according to that Dana system, composition, structure, lots of labels. Each one had a chemical formula and a locality and a crystal system and the name of the mineral. So I spent a lot of time studying that. And when we came up with this new system, one of the first things I thought was, wow, wouldn't it be more fun for most people to get the narrative of mineral evolution? And just last year, I was privileged to be at the opening of the new Hall of Gems and Minerals at the American Museum, which is arranged according to mineral evolution. So these ideas have already taken place. And it's not just at the American Museum. There's the Vienna Natural History Museum. There's Paris. There's the Tucson Mineral Museum, which is one of the major ones in the country. Mineral evolution is the theme in all of these. So this is really, really important to me because I think this is no way of teaching and understanding about minerals. But you've probably been thinking to yourself, wow, this is just a story. It's very qualitative. There's not a lot of numbers here, not a lot of rigor in that sense. And we need a more quantitative approach. And the way to do that is to harness deep time data, basically harness the known ages of lots of minerals. And so that was part 2 of this whole story, quantitative mineral evolution and building a database. So I went to my very good friend, Bob Downs at the University of Arizona. He runs what's called the RUF database. It has the official list of all IMA approved minerals. It has searchable chemistry filters. And what we did is working with University of Arizona graduate students and undergraduates, an army of undergraduates. We sort of by brute force built this mineral evolution database, which now has over 200,000 mineral locality age data, which means that you can look up your favorite mineral or you can look up your favorite time period and you can see how the minerals change through time. We focused a lot of our attention on the first row of transition elements. And as you know, they're really common in Earth's crust. Most of them are sensitive to oxygen. They play really important roles in biology, and they're also economically valuable. So they're good to study. And we got a total of over 60,000 mineral locality age data for these first row transition elements. And here's a plot. Now, in this plot, what you see on the horizontal scale is time going back 4 billion, 3 billion, 2 billion, 1 billion years. And here's the modern age over here. And on the vertical scale, you'll see the number of mineral locality occurrences in 50 million year bins. So there's a lot of information packed up here. The bins are also colored by the oxidation state, and I'll get to that. So what do we see here? The first thing we see is a very strong episodicity as a result of supercontinents. Supercontinents come together in what are called single landmasses or supercontinents, and then they start breaking up. So right now we're in a time when all the continents are sort of breaking apart from each other, but earlier, a couple 100 million years ago, they were all lumped together. And that cycle has taken place every 500 million years or so. And if you look at very robust minerals like zircon is a zirconium silicate that always incorporates a lot of uranium. And so you can date them very easily. And because they're so resistant, they form a large fraction of the heavy minerals that you extract from sandstones and sands and all around the world. You can find rare zircons, and they always show this periodicity. 5 big pulses associated with 5 episodes of supercontinents forming. Now, why should that be? It's because when you make a supercontinent, you make mountain ranges. The mountain ranges are mineral forming environments, and the mountains preserve those minerals. So you have a differential formation rate and also a preferential preservation of minerals from those periods. You always see these pulses, and we see the exact same set of 5 pulses in our data for any different kind of minerals, but there are all kinds of subtle differences, which I don't have time to go into now, but this is a really neat thing. Now, the second thing we look for is a change in the average oxidation state. For example, copper, it can be reduced in native copper. It can be in an intermediate form, copper 1+, and it can be more oxidized in copper 2+. And my colleagues have assembled all the copper data. They've looked at it, and what they find is this very dramatic increase in the more oxidized forms of copper in more recent formations. So this is a direct manifestation in the mineralogy of the oxygenation of the atmosphere. And we can plot all these kinds of data in fancy ways. This is called the skyline diagram. Here are all of the first row transition elements, and you can compare each to the next. You can look at their oxidation states, and there's just a vast amount of information that's embedded in this kind of diagram. So it's really exciting. We're just beginning to explore it. We, in fact, can do this for all of the chemical elements now from our mineral evolution database. You can pick your favorite element, carbon, for example, and you can look at it and you can see how the carbon minerals change through time. And this is all open access. This is all material on our website. So there's lots and lots of things you can explore. Now, there are other tricks we can play too, because we know the locality as well as the age of these different minerals. We can merge this with reconstructions of plates from early in Earth's history. G plates is one of our favorite, and we collaborate with the University of Sydney scientists who are putting this together. And so you can basically have a reconstruction of Earth over the last 200 million years. And you see the little yellow and black dots, those represent copper and uranium mineral occurrences, and they pop up exactly at the time when they form, and you'll see that almost all of them occur at plate boundaries. So we can really understand mineralization, and we can use this to help predict where new mineral deposits should be found. So this is stage 2, phase 2 of this whole process. We've seen that Earth's minerals display striking epidicity, and that's because of the supercontinent cycle. Now, what I didn't tell you about was the different chemical elements have very different, significant differences in the details in each of these 5 supercontinents. So they're not all exactly the same, and there's a lot to be learned there. Also, we see that redox-sensitive elements, especially these transition elements, display an increased oxidation state. But what I haven't told you is that you can actually correlate the depth of formation of these minerals, and therefore reveal not just about the atmospheric oxygenation, but also how quickly the subsurface environment has been changing. And that's really important for ore forming as well. So that's something new. So there's good news about this. I mean, this certainly provides a quantitative approach, but what it doesn't do is fully exploit the potential of mineral data. And so the third phase of this whole sequence is the effort to develop an evolutionary system of mineralogy based on mineral informatics. And this really involves analytical and visualization methods applying to data resources. So what do I mean? Think about minerals. Every mineral specimen contains an immense amount of information. There are dozens of trace and minor elements in every specimen. There are scores, hundreds of different isotopes, stable isotopes. There's structural defects. There's solid and fluid inclusions. There's the morphological, the size and shape, the physical properties, the petrologic context. So many different things that you can describe and measure as data. And so minerals are information rich, and it's those different attributes of minerals that tell you about the history of the planet. This is part 3, and it's what's been obsessing me the last 4 years, and it's probably the most exciting thing I've ever been involved in, I think. So first thing we need is lots of data resources, and I mentioned rough before, that's the list of all IMA minerals, but lots of links to other kinds of data. There's an incredible resource called mindat.org, which gives every mineral and locality. There's now over 1.2 mineral locality data in this, millions of photographs. It's an astonishing resource. And then there's a lot of classic printed materials, including literally tens of thousands of original articles that we can scan to get additional data about minerals. And so assembling all that and building data resources is one of our big objectives. So what these data allow us to do is new analytical approaches. And I'm going to take a step back now. I'm just going to show you some eye candy. These are various methods that we're using to exploit data in different ways, but they're just really pretty, I think. For example, a chord diagram. This has been used in biology for a long time, but never in mineralogy. And what this shows is, in this particular case, the 30 most common cobalt minerals. Each one of those minerals is an arc around this circle. And then every time an occurrence of one of these minerals co-occurs with a second mineral, there is a chord, one of these looping sort of things. And so you can see for every one of the common cobalt minerals, which ones does it commonly occur with, which ones does it rarely occur with, what kind of trends do we see in this? And those patterns reveal all sorts of things that allow us to make predictions about cobalt mineral deposits. You may know that cobalt is one of the the rare elements that's very much in demand because of battery technology these days. Here's the second kind of diagram. This is called a clay diagram. And in this case, this is a 72 by 72 matrix in which every matrix element says, if element number 1 is present, what is the possibility that the second element is present? And so you can see hotspots where you have combinations of elements like here. This is the coexistence of cobalt with arsenic. And there are far more cobalt minerals with arsenic than you would expect just based on their commonness in Earth's crust. Somehow those two elements like to find each other. And this tells us a huge amount of information about crystal chemistry, about the chemistry of Earth's crust. And you can see there's all sorts of information here. That's over 5,000 matrix elements. And every one of those matrix elements is a chemical story about Earth's crust. And we can do this in 3 dimensions now. This is a whole new kind of visualization that we invented for this purpose. This is a 30 by 30 by 30 clay diagram, 3-dimensional clay diagram with 27,000 matrix elements. And what it's basically asking is, if you have element 1 and 2 present in a mineral, what is the probability of finding element 3? And if the probability is what you find in nature is much greater than that probability, then you color these with hotspots. So you'll see, once again, you'll see a number of hotspots, these bright green sorts of things. Those are all examples of combinations of elements that occur much more likely than you'd expect from crustal abundances. I mean, this is several lifetimes worth of work to study and understand this diagram, but it's really amazing. And then my absolute favorite kind of visualization is called network graphs. Now, you're probably familiar with networks. You know, you're a group of physicists that like to get together, but each of you has your own other communities. You have family communities, you have neighborhood communities, you probably have, either a church or some other organization that you belong to, and those are other communities. And you can show those as networks of interacting people, knowing different people. Well, minerals are the same. Some minerals like other minerals, some minerals hate other minerals, and they never associate. And on this particular diagram, these are 37 different minerals that occur in what are called igneous rocks. Those are rocks that form from a melt. And you can basically see every common rock type. There's granite. You might have a granite countertop in your office. There's olivine basalt, as something that occurs in Hawaii, for example. There's nepheline syenite. That's another kind of rock. Every known igneous rock can be demonstrated as an interacting group of nodes of different minerals on this diagram. And so that's a very powerful way to represent. And we can do this with all sorts of things. Here are diagrams of the common chromium and copper minerals. The chromium minerals are colored by the way they form. Orange are igneous chromium minerals, for example. Green is weathering products. And in the copper mineral case, they're colored by composition. So red are the sulfides, and orange are the sulfates, and blue are the oxides and carbonates, and so forth. And you can understand how each mineral is linked to another, and you can see clusters of minerals, all sorts of things. We can do this in 3 dimensions. This is work of Dan Hummer on manganese minerals. And what you see here are some very interesting sort of side groups that represent up here. These are manganese phosphates that occur in pegmatites. The red color indicates that it's manganese in the 2+ oxidation state. 3+ is blue, 4+ is yellow, and you see lots and lots of different patterns here. If you're a manganese minerals expert, you can study this network diagram for weeks and weeks and weeks. And every time you click on one of these different nodes, you can find out more about how manganese minerals are distributed. Just really astonishing amount of detail. And you can even do this in virtual reality. This is a 3-dimensional virtual reality. My colleague, Shauna Morrison, looking at a network of carbon minerals, a particular kind of network. So much fun stuff to do. Okay, that was just for fun. That was for side. It gets you can see that there's ways of using and visualizing these data that tell you a huge amount. But the key idea of this talk, and what I really, if you take away one thing, it's that you can exploit these data resources, and you can develop a new system in mineralogy that reveals the coevolution of Earth and life. So this is different from the IMA system. And the way it's different is it differs from IMA protocols in 3 ways. In our system, sometimes IMA species are split into several natural kinds. In other cases, we lump a bunch of IMA species into one natural kind, and we also accept and classify species that are amorphous, things like volcanic glass which is not included in the IMA system because they don't have an idealized crystal structure. So you're eliminating whole classes of planetary materials just because you can't measure them with X-rays. That seems strange to me. So let me give you this idea of splitting. Diamond. In IMA terms, diamond is pure carbon. It's in the idealized diamond crystal structure. But when we look in nature, we find these tiny, tiny presolar diamonds. Those are from stars long before Earth formed. We have type 1 diamonds that form deep within Earth from an aqueous carbon-rich fluid. We find type 2 diamonds that form deep in Earth's mantle, this time from a metal carbon-rich fluid. We have impact diamonds. That's what happens when an asteroid hits a carbon-rich layer at Earth's surface. And then we have these strange things called carbonado, and nobody really knows how they form. But these are at least 5 different natural kinds of diamond. They have different properties, they have different characteristics. They look different, they feel different, even though they all have that IMA base of diamond. Now, apatite's another. Apatite's a calcium phosphate. You find it in meteorites. You find it as beautiful crystals and pegmatites, but also it's the principal mineral that forms your teeth and your bones. And I would argue that the biomineralized apatite is fundamentally different from these other 2 kinds. Pyrite is the single mineral that has the most different natural kinds that we've identified. There's 21 different ways that pyrite forms, each with different sets of properties. Some are at high temperature, some are at low temperature. Some are with aqueous fluids, some are with sulfide fluids. Some are biogenic, like this one in the middle, but others form purely in abiotic ways. So pyrite's really interesting. It forms in a lot of different ways. And so if we were to go to Mars and find pyrite, that would be interesting. But my first question would be, yeah, but what kind of pyrite? Because that tells you everything. Now, other minerals we lump. The IMA convention leads to something very strange and paradoxical, because if you have slightly different ratios of elements, a little bit more magnesium to iron or a little more iron to magnesium, those are 2 different species. A little more hydroxyl versus fluorine, a little more aluminum versus ferric iron. And if you look at one of these colorful crystals of tourmaline, you can have as many as 7 different IMA species in a single crystal you can hold in your hand. And that's, to me, just doesn't make any sense. So we lump these together. This can happen at a very small scale. Here's work by Ed Grew, my colleague. And this is a crystal that's less than 1 millimeter across, but it has 2 different tourmaline species because the ratio of iron to magnesium changes. So that's why we lump things together. Now, finally, volcanic glass, obsidian, or coal, or things called limonite and pyrolusite, all of which, by the way, Dana included in his system because that was before X-ray diffraction. But now with X-ray diffraction, none of these diffract X-rays, so they're not included in the IMA system. But they're very important from a planetary point of view, especially on Mars. I've been part of the Curiosity rover team on Mars, and what we're finding is 50 to 70% of the soils on Mars are amorphous materials that are just simply not considered by the IMA. But you can't understand the surface of Mars if you don't include those amorphous materials as part of your story. So we include them. Now, how are you going to systematize things? And 2 new papers that have just come out very recently are our attempt to get the overview of all of this evolutionary system on the paragenetic modes of minerals. A paragenetic mode is just a different way that things form. We also have a paper on lumping and splitting, and together these 2 papers give our philosophy. What this involves, and what every any research program you're going to do in mineral informatics, you got to build a data object. And this is so laborious. I did this during 6 months of COVID isolation. There's 5,700 minerals, each a different row in this column, in this database. There's about 57 different columns, each a different way that minerals form, and all the little zeros and ones, or the blanks and the ones, they represent a mineral, and it's different ways that it forms. So this took many, many months. There's 5,700 minerals. There are about 10,500 different ways that a mineral forms by a particular process. And this is the basis for the evolutionary system, which is now being published in parts. Part 1 looked at stellar mineralogy, and here you sort of see the core idea. Graphite is an IMA approved mineral. So is moissanite, that's silicon carbide. But there's always a prefix. This is a binomial nomenclature. AGB is a kind of star. Type 2 supernova is a type of star. So you link the mineral with the way it formed. And this allows you to make a network graph, what's called a bipartite network graph. In this case, the stellar type nodes represent different kinds of stars. And the little diamonds represent different kinds of minerals, and every mineral is linked to one or more stars. Every star is linked to one or more minerals. This is part one of the system, shown in a graphical representation. And this is the key, this idea, multidimensional analysis. Now, how do we know that those different grains come from different kinds of stars, AGB versus supernova? And here I just want to do a little sidetrack to show you what's laborious work is involved. These are done by my colleagues at Carnegie and University of Chicago and Washington University. And they basically take meteorites that are rich in these stardust grains. They dissolve them in acid. They get the silicon carbide grains in this case. They build huge databases. Here's a database with 17,000 analyses of silicon carbide. And the analyses constitute ratios of isotopes. And then you can illustrate those ratios of isotopes and plot them against each other, and you see these clusters of different isotopic ratios, each one of which represents a different kind of star. So we've been taking these data and doing more advanced work, this work by Asma Buyabar on silicon carbide grains and a new classification system, and we basically do cluster analysis, it's called, to identify different groups of silicon carbide grains that represent different natural kinds. So that's how we do it. And what we see is that there's several distinct environments in AGB stars. We see new kinds of effects from supernovas and so forth. There's a lot of physics that goes here. We've also worked on pyrite and see 7 different trace element patterns just from the pyrites from ore bodies. And we're building huge databases of garnet and feldspar and oxide spinel. When I say huge, I mean, in some cases, hundreds of thousands of chemical analyses, so that we can start doing cluster analysis and see what natural kinds are. So that's just where we're going. That's an ambition for the future. Here's part 2 of the system. These are interstellar and solar nebula grains. So we have the initial stellar minerals combined with, in this case, nebular minerals and interstellar ices of various sorts. So the network keeps expanding. Here's part 3 of the system. These are the primary minerals that form in the nebula. So now we're getting up to about 110 different minerals shown in this graph. We can add the alteration. This is what happens when you have impacts and aqueous alteration and thermal alteration. This is about 300 different species, all the things you find in meteorites, for example, and this. And then we can add the models that we have for the earliest Hadean, and this graph gets larger and larger and larger. It keeps expanding. But the original graph that I showed you, the one with the stellar minerals only, that's still a subset of this entire graph. That's still in there. Parts 1 through 6 are all here. We're working on part 7 now, and this just keeps going on. By the way, this graph, we think, is a very close model for Mars. And it's hard to imagine at this point any mineral that's on this graph that wouldn't be on Mars, or any mineral on Mars that wouldn't be in this graph. So that's our hypothesis right now. Now, fast forward, because we can't go through all 10 stages, and there's just a lot going on here. This is our ultimate graph of all of mineralogy. This is a network diagram with 5,700 little brown dots, each representing a different mineral species, and 57 nodes, larger nodes, that represent the different ways that minerals form. And so there's a huge amount of information in this. This is just a remarkable diagram. I should point out one thing. A lot of minerals form by only one process. All these big fans that make this so beautiful, all these fans out here, they're all connected just to a single mode of formation. But in the middle, we have several hundred minerals that form by more than one way. And so they're in the middle because they have to be linked to multiple things. And that's just the structure of this kind of bipartite graph. Really quite amazing. So let me tell you 4 things that we've learned, and that's sort of where I'm going for the rest of this talk. The first one, and this to me was really striking, water is absolutely the principal driver of mineral diversity on Earth. more than 80%, and probably if you analyze it in more detail, it's going to be more than 90% of all the species of minerals on Earth arise because of some kind of water-rock interaction. That's pretty amazing. Now, the second most important thing is biology. Biology can form more than half of all the species known on Earth, just through biological processes, directly or indirectly. But what's more than a third of all the mineral species on Earth are exclusively known to form through biological processes. Now, that's just really a remarkable statement. Now, here's something that this just really blows me. 42% of all minerals, 42% of the minerals require one or more rare element. And I'm talking about 41 rare elements that collectively, if you take all the rare earth elements and the platinum group elements and arsenic and molybdenum and tin and lithium and boron and beryllium and cesium, if you take all those elements, combine them, they collectively represent only 1 in 10,000 crustal atoms. So a tiny 100th of 1% of the crust. And yet 42% of all mineral species that are known require one or more of those elements. So these incredibly rare elements are disproportionately controlling the mineral diversity on Earth. And I think that this is another reflection of the importance of water-rock interactions, that water selects and concentrates elements and then brings them to places where they get highly concentrated. And so you can have rare minerals of tantalum or cesium or rhodium, for example. Really surprising, but that's part of the characteristic that we see on Earth, and we see it no place else. And finally, I want to propose a hypothesis. And the hypothesis is that the structure of this network is not just demonstrating minerals on Earth, but I think that the actual network topology is a planetary scale biosignature. I think if you look at the minerals on Mars, which don't have this characteristic, that the network topology is very, very different. So this is a hypothesis that minerals themselves are a biosignature, and we are exploring that in quite a bit of depth. So this is my conclusion. It's pretty simple. I think we're entering a new age, an age of mineral informatics. And it's the multidimensional analysis, the visualization of mineral systems. That's what's going to lead us to insights and predictions about the coevolution of Earth and life. With that, I thank you very much for the chance to talk to you, and I hope there might be time for some questions.
Well, thank you very much for the presentation. Does anybody have any questions here?
I do. I've been reading the book by Nick Lane called Transformer, and of course he has a different purpose in that particular book, talking about the Krebs cycle and so forth. But all of his books emphasize this relationship between minerals and life that you've proposed. And what surprises me is I don't see that story being talked about very widely. I've only seen it in Nick Lane's books. And so what's going on there? Is this a widely accepted proposition that you have?
Please unmute.
You're on mute.
Your mic is
Please
muted, Bob.
unmute.
I wasn't muted for the whole talk, was I?
No.
That's funny. I don't see how that happened.
I
Anyway,
pushed the wrong.
so I think that, first of all, it's a fairly new idea. The paper came out in 2008. And if you look at the citations of that paper now has something like 600 citations. But if you start at 2008, it started very slowly. Now it's sort of exponentially going up year by year. So the original paper and the ones that followed are getting much, much more attention now than they did, say, 10 years ago. Also, I think that it's really requires people in different fields, in the geosciences and the biosciences and astrobiology, to sort of be familiar with multiple literatures, which they're not necessarily comfortable with. So most biologists don't think about minerals, most mineralogists don't think about biology. And that just has to gradually change. These planetary systems are so complex, they're so intertwined that I just see this as being, there will be an evolution of thinking, which is that's the way science works, you know? What surprised me most is that very quickly the mineralogical community, which is not used to thinking about words like evolution and coevolution of the biosphere, the two top prizes in the field, the Roebling medal and the IMA medal, both came pretty quickly after that, and that surprised me because I thought that it would be more challenging to the community, but mineralogy has been kind of on hard times recently. Sense that most universities are dropping their mineralogy professors, maybe not teaching mineralogy as a separate subject, and so you need to have a broader perspective to bring this in.
I have a question.
Are you in a position to predict anything about searching the atmospheres of external planets to be an indicator of life that's different than, say, just pure oxygen or something like that?
Oh, that's really interesting that you should ask that. One of my gifted early career people, Michael Wong, just was named a Hubble Fellow, and he's working with me for the next 3 years. He's using these same network techniques to model different atmospheres. And the kinds of topologies we're seeing in the mineral sphere that point to biosignatures, we think also are present in the networks of atmospheric molecules, which molecules are associated with which. So we're thinking very, very closely about network structures and atmospheres. And when you say predictions, that's one of the things that these approaches really allow, that you can not only say what's where and how are they distributed in a quantitative way, but you can also make predictions about what we've overlooked. And so we actually predict the specific locations of certain minerals and have sent collectors out, and they found them in places that had not previously been described. So we, turning mineralogy into a predictive science is part of our goal, and getting away from that famous old quote, "Gold is where you find it." We want gold to be where you predict it's going to be found.
Great.
When did minerals start to form? Did they start to form in the solar nebula before the planets formed? Or
Minerals certainly condensed before there were planets.
okay,
But even before that, there's stardust, these particles that are less than a micron across in most cases. And very recent work has actually been able to date some of these individual tiny grains. The oldest one I've seen so far is 7 billion years old. So that must have formed around a star 2.5 billion years before our solar system even began forming. And I've heard rumors that someone has found a grain that's 12 billion years old. And this is submicron size. So it's a very, very tiny object, but it was formed in a star within the first 3 billion years of our solar system. That's just an incredible thing to say.
I found that this talk very fascinating. Where can I get some summaries of your, what it's just the American Mineralogist papers?
There's a lot of papers in American Mineralogists, but there's other, my website. So if you just Google Robert Hazen, our website has a lot of information.
Okay.
I probably haven't updated that in now it's probably close to a year. So some of the most recent stuff isn't there, but the basic ideas are available on websites. There's a Scientific American article.
Oh, okay.
There's a NOVA episode that came out a few years ago called Life's Rocky Start. You could just get that online. So
Okay.
there's a lot of kind of, and visit one of those great museums, look at the American Museum of Natural History or the Tucson. If you ever go down there, there's some, they're doing wonderful jobs in presenting this to a broader audience.
Okay, good, very good. Thank you. Yeah, I volunteer at Air and Space, and the young woman I work for actually has a background in geology, and I'm going to tell her about this. She's going to get crazy when I tell her about this.
Oh, that's great. Yeah. Well, we love to spread the word. That's
Yes.
So are there anything, any minerals that are non-natural?
Well, that's stage 11 we talk about, this whole idea of what's been called the Anthropocene epoch, which some geologists have been pushing that some people say it should be the last 10,000 years, the last 2,000 years. Some people say it should be since 1940s, when there's a marker layer of radionuclides from the nuclear testing. But there are definitely isotopic and mineralogical record that humans have left. And just, we make bricks, we make laser crystals, we make all these objects. And yes, there are thousands of mineral-like materials that are not recognized by the IMA as official minerals, and yet they will become part of the geological record. And 100 million years from now, some of those materials will still be present, and they will provide a reference layer in the sediments of human activities that document this time in geological history. So I've written a paper about the mineralogy of the Anthropocene epoch, and that's one of my most cited papers. It's very interesting. It's a very political issue because the people who want to call this the Anthropocene are trying to make the point that humans change the environment. And people who do not want to recognize the Anthropocene are saying, no, this is just a passing little thing, and it's not a. So it's become a political football, and I don't get in the middle of that, but it's certainly true that there are mineral-like compounds in abundance that have been produced by society.
And if you find them out in space in an exoplanet or something, is that proof that there exists aliens?
Well, we certainly think there's some phases that are unlikely to form without some kind of intelligent intervention. For example, if you have a mineral that's rich in rare earth elements and the distribution is such that you have 99% praseodymium. If you're familiar, the rare earth elements, there's 14 of them and they all behave chemically the same, and nature just doesn't differentiate them very well. So if you had a very high concentration of just one of them in a compound, I think that would be pretty much clear evidence that there have been some intelligent processing of those materials. So one can imagine inorganic compounds that were biosignatures, but it's going to be a while before we're able to find those and study them in that kind of detail.
Mm-hmm. Thank you.
I just found a collection of rare earth elements in the state of Maine.
Really?
I just saw it in the news today.
Wow. Well, that could be very important. Those are absolutely critical resources to.
Yes, and the Chinese are sort of have a lot of them.
They have a lot of. We have a lot of them too, but we have such rigid rules about environmental protection. There's a very, very large deposit of rare earth elements in California, but it's just been environmentally difficult to exploit it. But Maine, I'll have to look that up. That's very interesting.
Any more questions? Well, want to thank you for really a fabulous talk, taking us billions of years across and many miles.
Yes.
Oh,
That was great.
again, thank
Really
you.
enjoyed it.
Thank you so much, everyone.
It was very good.
And appreciate your interest and wish you all the best.
Thank you.
Okay,
Thank
Take
you.
care
Take care.
and have a good trip to Rutgers.
Thank you. Thank you. Leaving very soon. Shit. Bye-bye now.
Bye.
Bye.
Thank you.
That was certainly a fabulous talk.
Indeed.
It was amazing.
Yes.
See, I
I'm
think we
glad I
had
know
what-
you guys.
We had 15 participants, which is more than we usually have. So that was good too.
Especially on Zoom. And we had a steel maker too. I thought this was really interesting. I mean, if you find a sword, you know there has to be a swordsmith. If you find some steel, you know there has to be a steel maker.
Right.
And those aren't classified as minerals exactly either. But they have minerals in them.
Yeah. Well, there's more to learn than just the periodic chart.
Yeah. And more to learn than just the quarks if you go backwards. And the neutrinos and the leptons and even the ones that persist for a while.
Yeah. Well, from space, it's good to get back to Earth from once in a while for our talks.
Yeah. But Earth is connected to all of these things.
Yeah.
I mean,
Well,
Let's see.